Swayam Prabha. Digital India. Educated India.
Hi friends, now we will discuss on the second part of the module energy production from waste through pyrolysis. In the first part of this module, we have discussed on the fundamentals of pyrolysis, reaction mechanism, different products, applications of bio oil and catalytic pyrolysis, and in this module we will discuss on the pyrolysis reactors and utilization of pyrochar and gases. As the pyrolysis is one thermochemical conversion process, like other two thermochemical conversion process like incineration and gasification, in this process also the first reactor was fixed bed reactor, and then fluidized bed reactor and circulating fluidized bed reactor was developed. In these three reactors, that is fixed bed, fluidized bed and circulating fluidized bed, some sweep gas is used. In case of combustion and gasification, combusting agent and gasifying agent are used, but in these reactors no such agent is used, but inert gas is used to carry the pyro vapor which can be further condensed. Thereafter, some development came with the reactor to avoid the use of inert gases. So, ablative reactor and then came rotating cone reactor, then came vacuum pyrolysis reactor and auger or screw reactor. Now, we will discuss one by one on these reactors. At first, we will see the fixed bed reactor. In the fixed bed reactor, the waste or biomass can be put from the side top of the fixed bed, and in this case this zone will be heated zone, and we need to send one inert gas, that is sweeping gas. And as the temperature is maintained here, biomass and waste is coming here. So, pyrolysis will take place, but here the diameter of the particles may be bigger, no limitation on the diameter of the particles. So, when it is coming in this hot gas, then vapors will be created through pyrolysis and it will goes off, and further it will be cooled and we will get bio oil and the gases. It gives 30 to 50% of bio oil and gives more char, because it gets more residence time. We are not using here any heat transfer media like sand, unlike other fluidized bed and circulating fluidized bed. Say sand is used so that it has high heat transfer coefficient, and so rate of heat transfer is more in those reactors, but here the rate of heat transfer is less, and basically solid gas to solid heat transfer takes place. There is no solid heat transfer. That is why the time requirement is higher, residence time is higher. As a result, the char production is also high here. More char is produced and less bio oil is produced. But this is very simple process and it is reliable, but because of low oil production, bio-oil production which is more desirable in pyrolysis reactions, this is not commercially used much. Next, the fluidized bed reactor came. In fluidized bed reactor, the biomass or the waste is put from the bottom and the sweeping gas is also from the bottom, and particle size of this is very less than 2 millimeter. So, because of this very low particle size and supplying from the bottom, it gets more mixing with the hot gas and residence time is also less. Due to that reason, the bio-oil production is more. In this case, we can get around 70 to 75% bio-oil, and rate of heat transfer is also very high in this case, because particle size is less and we use some sand. So, sand is used. So, sand helps solid to solid heat transfer and gas solid as usual it is also there. So, convection, conduction and radiation, all the three mode of heat transfer acts on this, and 90% conduction, 9% convection and 1% is radiation. And heating takes place, this gas which goes off, that can be recycled, because this will also carry the char, this is also will carry gas, vapor, char and sand also. So, this can be recycled back. So, that is why the heated recycled gas, hot inlet gas, both helps for the heating of the material, as a result the pyrolysis of the material. The design is simple. The advantage is that the design is simple, it is easy to operations and it can be suitable for a large scale production. But the main disadvantage of this process is that it requires smaller particle size, minus less than 2 millimeter. Next, we will come to circulatory fluidized bed reactor. In circulatory fluidized bed reactor, two chambers are used. In the first, we put biomass or waste, and here we put recycling gas, recirculating gas. Recirculating gas, where from it comes? It comes from the second chamber. So, here the pyrolysis takes place. So, pyrochar along with vapor, gas, char and sand, so all comes from the top of this pyrolyzer, because high velocity is maintained here. So, it is coming, then it is separated, and this part is sent to other chamber, that is chamber 2, and we pass here oxygen or air, or we pass here air. So, air helps to combust the sand, char it coming here and mix some flue gas, that gas is used for heating here, and the material which is produced here, that can also be recycled here, the sand is recycled here. So, this is the development of the fluidized bed reactor. The some part is recycled, the solid is recycled. So, heat transfer is taking place here through the conduction, convection and radiation, and this char or the sand which is returned, that can act as some catalyst also, that will be having some catalytic activity. So, due to this reason, here the bio-oil production is also very high, 70 to 75% bio-oil production, and here conduction mode, contribution of the conduction mode of heat transfer reduces from 90 to 80% with respect to fluidized bed. Due to the circulating effect, conduction mode is 80%, but convection mode increases from 10 to 19% and radiation remains same around 1%. So, this is the mode of heat transfer in this reactor, and here some in bed gasifications takes place and heated sand helps for the heating of this. So, these are the basic features of this, but this reactor has some disadvantage, that is its complex hydrodynamics in it, and it is unlikely to be suitable for large scale production. Next we will come on the ablative reactor. In ablative reactor, one hot plate is used and it is rotated, this is rotated, and biomass is put on it and waste is put on it and it is pressed, and it is pressed. So, due to as shown here, so this is pressed. So, hot plate increases the temperature here and the biomass or waste is converted to vapor, gas and aerosol. One disadvantage of this process is that how to heat the system. Like other cases we use hot gases, but here we are not using any hot gas, we are heating the plate only. So, how the plate will be heated, that is the main problem here, and this is advantage is that this is a compact reactor, it is a compact reactor and it does not require any sweeping gas. So, that is the another important advantage of this reactor, but disadvantage is that how to heat the biomass. So, that is the main disadvantage, and this is not commercially used yet, and in this case we see maximum heat transfer takes place through conduction. So, 95% is conduction, 4% convection and only 1% is radiation, and solid heat transfer takes place. There is no gas solid heat transfer in this case, and inert gas is not required, but this reactor is costly and low reaction rate. So, these are the disadvantage of this reactor system. Next we will come to rotating cone reactor. In rotating cone reactor, one cone shaped reactor is used. In this cone shaped reactor, it is rotated and we add waste or biomass from the top and also sand, that is hot sand. We also put hot sand and this, and there is some centrifugal action on it. So, the material, the waste biomass and hot sand get mixed. So, heat transfer is very fast. So, as the hot sand is used and the material, but the product comes out from the bottom. So, it takes less time and we get here vapor, gas, char, sand, and after separation sand is can be added from the top once again. In this process we can get around 65% of bio oil, but this reactor system also has some disadvantage, it is difficult for scale up. Next we will come to vacuum pyrolyzer. So, vacuum pyrolysis reactor, in case of fixed bed pyrolysis reactor, we had seen that material is in a lower part of this reactor. Now, if we do not flow the sweeping gas, in spite of that, if we put some vacuum here, we can put some vacuum here and material can be put into trays, different trays as shown here, the different trays. So, this material can be put in different trays and some vacuum is created here, so that we do not need to provide any inert gas to carry the vapor produced inside the pyrolyzer. We can put the material from the top, in this case like fixed bed reactor, and but due to the application of vacuum, it generates vapor at lower temperature and it is easier for liquid productions. So, these are the advantages, and disadvantage is that this is slow process, solid residence time is too high, just like fixed bed. So, it requires large scale equipment and generates more water. Here bio-oil production is also similar to fixed bed reactor, say 35 to 50%. That is why this is also not very widely used. Next, another development on this pyrolysis reactor is auger or screw type reactor. In screw reactor we use two tank, one containing hot sand and another is containing waste or biomass. So, these two are mixed. After mixing it goes to a screw. So, we have some screw shaft and it is going through the screw. So, from the other end when the material is coming inside and it is giving by some motor action and this it is giving, the screw is giving forward movement to this material. So, this is also hot in heated, this is also hot sand. So, after mixing this hot sand and waste it is coming to screw and it is going forward direction and pyrolysis is taking place here. So, from the top the vapor gas goes up and from the bottom we collect sand and char. Here also sand is added. Advantage of this reactor is that we do not need any inert gas flow, and it can give around say 30 to 60% of bio-oil production. Next we will go on plasma reactors. So, after ablative, rotary cone and this screw reactor, the people are trying to develop new type of reactors which may be more efficient, and just like plasma gasifications, plasma pyrolyzer is also being attempted to be developed, and in this case the condition will be different, that plasma will be produced in the reactor just like plasma gasifier by applying high voltage, applying high voltage across two electrode, and that under certain conditions those plasma will help to vaporize the materials which is inside this, the waste and biomass. So, the vapor will form that can be condensed further and then bio-oil can be produced. So, this is the mechanism for the plasma reactors, and 30 to 40% bio-oil can be produced from this reactor. Now, we will see different reactors and we will compare some parameters. Now, say type of reactors. Fixed bed, fluidized bed, circulating fluidized bed, ablative, rotary cone, vacuum and auger. If these are the type of reactors, then if we see which one is commercial. So, fixed bed is not commercial, fluidized bed commercial, circulating fluidized bed also commercial, ablative is lab scale, rotary cone is demonstration scale, vacuum is also not in widely reported, vacuum is not widely reported, and auger is in pilot scale, this is in pilot scale. So, these are the status of in which level these reactors have been matured and applied. Next we see the bio-oil productions. So, fixed weight, that is 30 to 50%, here around 75%, this is also 75%. Ablative will give us about also 75%. Rotary cone is giving us 70%, and vacuum will give, it is similar to this, slightly say 60%, and auger is giving us 60%. So, these are the bio-oil production, and here if we see the complexity, out of these reactors the maximum complexity is with CFB, circulating fluidized bed, and rotary cone. Then for fluidized bed it is medium, auger it is medium, and ablative is high complexity, and vacuum is also high complexity. So, one is complexity parameter, and another important parameter is specific reactor size. So, reactor size is also medium for fluidized bed, CFB is medium, rotating cone is low, ablative is low, auger is low, and vacuum is high. So, ease of scale up if we think about, then obviously that fluidized bed is easy for scale up, CFB is easy for scale up, but ablative is not so easy, it is very difficult, and auger is medium. That screw reactors is also not so easy for scale up, but it is medium, it can be done. So, and feed size specification, fluidized bed is highly very particle size should be less than 2 millimeter. So, highly specific to feed size, but others like say rotary cone, it is having feed size specification is high, but ablative has no that of specification for feed size, any feedstock can be used. So, pyrolyzed vacuum can also be, any feedstock can be used. So, this table gives us some comparison on this feed size specification, inert gas requirement, a specific reactor size, etc. On the basis of these informations, it seems that the auger or screw type reactors which is having the medium scale up difficulty and medium complexity and medium size specifications, that may be of superior, but as it is developed in later stage. So, in future this reactor may get more interest. As on today, the fluidized bed reactor is mostly used in commercial application. Now, we will see some reactors used in pyrolysis processes. There are some report available on 2012. On the basis of this report, it seems that as per on 2012, different types of pyrolysis reactors have been used in different countries, here the Canada, UK, Netherlands, Germany, USA, China. In different countries the pyrolysis reactors have been used, and all those reactors is having capacity more than 10 kg per hour. So, here we see that these reactors are either in operational or commissioning stage or upgradations or in design stage or under construction stage. So, it seems that this technology is gradually coming up, it is developing, and different technologies like say fluid bed, auger, rotating cone, ablative, all have been used, but fluidized bed has been used in maximum cases, and circulating fluidized bed and fluidized bed have been used in many cases. So, now we will discuss on the application of char produced through the pyrolysis process. So, char which is produced from pyrolysis process, that can be used for different applications. It can be used for the fuel, solid fuel. This char which is produced, we have discussed in the previous module that its heating value is more than the biomass and waste which we use for the pyrolysis process. So, this can be used for a fuel, solid fuel, and can be used as soil conditioner. soil conditioner or fertilizer. The pH of this char is around 8 to 9. So, basic nature it has some basic nature. So, any soil which is acidic in nature, this will help to neutralize the pH and condition the soil. Second is, this is containing carbon and porous in nature. So, carbon, high porous carbon is present in this char, and this material's porous carbon remains for a longer time. In soil, it remains for a longer time in soil. As a result, it helps the diffusion of oxygen into the soil. So, that way it helps as the soil conditioning. Third application of char may be activated carbon production. Although this char is having some porous structure, but further porosity can be increased by activation. So, activated carbon can be produced by further activation of it. So, for the activation of this char, there are two basic methods, one is physical and another is chemical methods. In case of physical method, this char is heated, it is 800 to 1000 degree centigrade. In presence of some oxidizing agent H2O or CO2, this char is heated. So, due to this reason, the tar present in it is burnt off and carbon present in char is also further oxidized. As a result, the skeleton of this char gets more porosity. So, by this physical method we can increase the porosity of this char, and the porosity can be achieved say 500 to 2500 meter cube per gram. But in chemical method we use some chemical like say potassium hydroxide, phosphoric acid or zinc chloride. So, these three chemicals have been reported to use for the activations of this pyrochar, and it gives more porosity, but these have some disadvantages. These are the chemicals, and ZnCl2 particularly is very toxic also, and it requires washing, several times washing, and when washed it generates large number of waste water. Third is, if washing is not completed, then also there will be some possibility of leaching. So, because of these three difficulty, the chemical method is not getting so interest. The physical method is becoming superior than the chemical one. The reactions which take place during physical methods is that C plus H2O, then it will give CO plus H2, CO plus half O2, it will give CO2, and then H2 plus half O2, this will give H2O, and C plus O2, it will give CO2, and CO2 plus C, it will give 2CO. So, these are the reactions which takes place in case of physical activation. Now, we will discuss on the utility of the gas produced through the pyrolysis process. So, gas which is produced through pyrolysis, it contains CH4, CO, H2, CO2 etc., and its heating value is around 6.4 to 9.8 megajoule per kg. So, this gas can further be used for heating something. In this case, it is used for the heating of the gas in the pyrolysis reactor. So, these are the applications, important applications of this gaseous products. Or as hydrogen and CO is present, we can separate the hydrogen and it can be used for other applications, or COH2 can be used for other applications. So, after this in this module, so thank you very much for your patience.